A magnitude 5.3 earthquake just struck near Mati, in the southern Philippines, a region still standing in the wreckage of a massive earthquake from earlier this month. Officials are calling it an aftershock. The number attached to it is not 1, it is 7,561. That is the count. The Philippine Institute of Volcanology and Seismology has been quietly updating since the morning of June 8th. 7,461 tremors, one continuous sequence, no clear end. Somewhere inside that number sits a question seismologists cannot yet answer. Not whether the ground will move again, it will. The question is when this number stops climbing, and the honest answer is one most broadcasts will not say out loud. Stay until the end, because the reason that number cannot stop climbing goes back 50 years, and it changes what this earthquake actually means. If this has you thinking, subscribe to Rupture, because this is the kind of story the daily broadcast does not have time to tell you in full. Drop a comment below. When you hear the word aftershock, do you picture one event or do you picture thousands? Part 1. The morning. The ground moved again. At 6:57 in the morning, Manila time already well into Wednesday evening back home, the ground 1 kilometer south of a small coastal community called Kablalan moved for the second time in 11 days. The United States Geological Survey logged the event almost the moment it happened, assigned it the catalog identifier S7000USU9F, fixed its magnitude at 5.3 on the moment magnitude scale, and placed its focus 95.3 kilometers beneath the surface of the Earth. The agency marked the record reviewed, which is to say a human seismologist had looked at the waveform, confirmed the automated reading and signed off. It was not a guess, it was not preliminary. It was the kind of entry that becomes part of the permanent global earthquake catalogue the moment a duty scientist clicks save. That entry is a single line of data. But that single line tells you almost nothing about what people on the ground actually felt. Here is what that single line is hiding. A magnitude 5.3 earthquake on its own is not unusual. In the global record, the planet produces something on the order of 1,500 earthquakes of that size every year, which works out to roughly 4 every day somewhere. Most of them happen under ocean trenches no one is standing on, beneath mountain ranges no one is living under, and the world goes about its business without ever knowing. A 5.3 is not the size that flattens buildings. A 5.3 is the size that rattles plates in a cupboard, sloshes the water out of a half-full glass on a kitchen counter, and wakes light sleepers if it strikes during the night. It is the size that becomes a story only when it happens somewhere it should not, or to a place that has already been hit. Kablalan is one of those places. 11 days earlier, on the morning of June 8th, the same general stretch of southern Philippine seafloor moved with roughly 500 times more energy released than what the residents of Kablalan felt on Wednesday. That earlier earthquake will be the subject of its own part of this investigation. For now, you need only hold the geography in your mind. Mati, Davao Oriental, Kablalan. A coastline that faces east into the Philippine Sea, with thousands of meters of open ocean trench falling away from it, and a tectonic boundary running parallel to that coast that has been slowly grinding itself into stress for the entire span of recorded human history. When USGS placed the depth of Wednesday's event at 95.3 kilometers, the number is doing more work than it appears to. 95.3 kilometers, which is to say roughly the straight-line distance from downtown Manila out past the edge of its own metro region, except instead of measuring across the surface, you're measuring straight down through solid rock. That is a deep earthquake. The crust beneath the Philippines is not 95 kilometers thick. The fault that moved on Wednesday morning is sitting inside the upper mantle, inside material that, at the temperatures and pressures present at that depth, behaves more like extremely cold modeling clay than the brittle stone you walk on. Earthquakes that occur at that depth are called intermediate depth events. They happen because a slab of ocean floor is being shoved downward into the mantle along a steep angle, and as it descends, it bends, it heats, and at points along its length it cracks under the load. That is the deep event. Now look at the second one, because Wednesday morning, June 18th, did not produce only one magnitude 5.3 earthquake, it produced 2. The second occurred near the municipality of Bobon, on a different stretch of the same general fault system, and the magnitude reading was identical. 5.3. The depth was not. The Bobon event was logged at roughly 10 kilometers below the surface. 10 kilometers. That is the depth of a commercial jetliner at cruising altitude, except instead of being above your head, The rupture point is below your feet. That is a shallow earthquake by every meaningful definition the science uses. 2 earthquakes, same magnitude, same morning, same general country. One of them is hiding 95 kilometers down inside the earth. The other is sitting almost at the surface, and the people standing on the ground above each one are getting 2 completely different experiences out of an event that the headline reduces to the same single number. Here is why that matters. When an earthquake releases its energy, that energy has to travel from the point of rupture, called the hypercenter, up through the rock to where you're standing on the surface. The deeper the hypercenter, the more rock that energy has to push through, and rock, like a thick wool blanket between you and a loudspeaker, absorbs and scatters that energy along the way. A magnitude 5.3 happening 95 kilometers down is going to feel, to a person standing directly above it, like a long, low rolling motion that lasts longer than expected and is felt across a wider footprint, sometimes hundreds of kilometers in every direction, but does not actually shake any single building hard enough to do structural damage. A magnitude 5.3 happening 10 kilometers down does the opposite. The energy has almost no rock to travel through. It arrives at the surface as a hard, sharp, vertical jolt. The shaking is intense. The footprint is small. The people directly above it feel as though somebody dropped the building an inch. The people 50 kilometers away feel almost nothing. 2 earthquakes, 2 warnings. The same morning was telling Mindanao 2 different things about what was happening underneath it. For the people in Kablalan, the deep event was a long roll that lasted longer than the locals expected, that they likely felt in their chests as much as in their feet, and that anyone who was awake remembered for the rest of the day. For the people closer to Bobon, the shallow event was a sharper, more localized strike, the kind that knocks a picture off a wall in one house and leaves the house 3 doors down completely untouched. Both of those experiences are real. Both of them came out of the same morning. Both of them are buried inside the same headline number you read on Wednesday afternoon. Now zoom out from the 2 events for a moment. Look at the calendar. Wednesday, June 18th, is the 11th day of a continuous seismic sequence that began on the morning of June 8th with an earthquake hundreds of times larger than the 2 we just walked you through. In the intervening 11 days, the ground beneath the southern Philippines has not stopped moving. The instruments have not stopped recording. The duty seismologists at the Philippine Institute of Volcanology and Seismology, the agency Filipinos refer to by the acronym PHIVOLCS, have not stopped sending out bulletins. 2 new magnitude 5.3 events, on the same morning, 11 days into the sequence, are not a coincidence. They are not bad luck. They are a fault system telling you, in the only language a fault system has, that it is not finished. Let me show you what one of those bulletins looks like. When PHIVOLCS sends out a notice on an earthquake of this size, it includes a magnitude, a location, a depth, a tectonic origin classification, and an expected damage and aftershock advisory. The June 18th bulletins for both events said the same thing in the damage line. No damage expected. They said the same thing in the aftershock line. Aftershocks expected. They did not say how many more. They did not say how long. They could not say. We will get to why later in this investigation. For now, hold on to this. 11 days in, the official agency is still writing aftershocks expected on every bulletin it issues, and the count of those aftershocks has now climbed past a number most viewers would not believe if they saw it written without context. Out in the coastal communities along the Davao and Sarangani coast, the people who are standing on the ground on Wednesday morning know exactly what we're talking about. A farmer in Davao Oriental, the kind of man whose entire working life is conducted outdoors and whose internal record of the weather and the ground goes back 50 years, does not need a seismograph to tell him the earth has been twitching for 11 days. He has felt it under his feet while he was walking between rice paddies. He has felt it in the legs of his plastic chair when he sat down for lunch. He has watched a clay water jar shift sideways on a shelf without anyone touching it. This is the human scale of what 7461 actually feels like. We will get to the number itself in the next part. The question we are leaving you with from part 1 is the one we opened with. Why are 2 earthquakes of identical magnitude, on the same fault system, on the same morning, producing 2 different stories under the same single headline number? The headline is telling you the magnitude. The depth is telling you everything the headline is missing. And the morning itself, taken as a single piece of evidence, is telling you something about a fault that nobody on television seems willing to say out loud. Part 2, the number nobody printed. Remember the number we opened with, 7,461. Now let us show you where that number actually comes from, and why almost nobody is saying it on camera. That figure is not a guess. It is not an estimate by an independent researcher. It is not an exaggeration produced by social media. It is the running tally maintained by the Philippine Institute of Volcanology and Seismology, the same government agency that issues every official earthquake bulletin in the country, and it is updated almost in real time on their public-facing channels. The number has been climbing hour by hour since the morning of June 8th. As of the bulletins published in the days leading up to and including Wednesday, June 18th, the count of aftershocks recorded along the Cotabato trench sequence stood at 7,461. That is not one earthquake. That is a sequence. Let us put that figure into a household frame, because the number on its own is so large that the mind slides off of it. The human brain is not built to take in 7,461 of anything. It rounds. It collapses. It says a lot, and then it stops processing, so let us not let it do that. 7,461 earthquakes spread across roughly 11 days works out to an average of 678 earthquakes per day. That is one earthquake roughly every 2 minutes and 7 seconds, day and night, without pause, for 11 straight days. While you were eating dinner, the ground beneath the southern Philippines moved. While you were brushing your teeth, the ground beneath the southern Philippines moved. While you were sleeping last night, the ground beneath the southern Philippines moved an average of around 300 times between the moment your head touched the pillow and the moment the alarm went off. The vast majority of those tremors were small. Most of them were below the threshold where a human standing on the surface would feel anything at all. They show up on a seismograph as small wiggles, the kind of wiggles a duty scientist scans through by the hundreds in a single shift. But they are real earthquakes. Each one is a fault surface, somewhere along the ruptured zone, slipping by a centimeter or a fraction of a centimeter, releasing the energy of the original event in tiny, irregular installments. Now hold that frame in your head, the wiggles by the thousands, and let us add the parts of this number that are not small. Buried inside the 7,461 tremors are 3 earthquakes that PHIVOLCS classified at magnitude 6.0 or greater. 3. A magnitude 6.0 is not a footnote. A magnitude 6.0, occurring at shallow depth, is the size that pulls walls down from old masonry buildings, knocks chimneys off houses and sends boulders rolling down hillsides. 3 of those, hidden inside the larger number, would each be a national news story on their own in many countries. In the Philippines, over the past 11 days, they were absorbed into the running count and treated as simply another reading on a long bulletin sheet. That is the scale of what the daily broadcast is missing. Think about it this way. Imagine a thunderstorm. Now imagine that the thunderstorm did not stop after an hour or a night or a long stormy weekend. Imagine that the thunder kept rolling for 11 straight days, and that every few hours, somewhere along its path, lightning struck a building hard enough to set it on fire. You would not call that a thunderstorm anymore. You would call it a season. You would call it a climate. You would change how you lived your life until it ended. That is what a 7,461 event aftershock sequence is. It is not weather, it is climate. Now consider how this number is even gathered, because the mechanics of counting matter when the count is this large. PHIVOLCS operates a network of seismic stations distributed across the Philippine archipelago, instruments buried in concrete vaults, wired to data lines that feed back to the central office in Quezon City. When the ground moves anywhere within the network's range, the instruments detect the arrival of seismic waves, the first arrivals being the fast-moving P waves, which is to say pressure waves that compress the rock in the direction of travel, followed by the slower S waves, which is to say shear waves that move the rock sideways. By measuring the time gap between the P wave arrival at multiple stations, the network can triangulate the location of the rupture, calculate its depth, and estimate its magnitude. For a single earthquake, this process takes minutes. For 7,000 of them, in 11 days, it requires duty scientists working in shifts around the clock, automated detection software running continuously, and a manual review queue that probably has not emptied since the sequence began. Every entry in that 7461 event log is a piece of work. Somebody saw it, confirmed it, located it, and added it. Multiply that by 7,000, and you have a sense of what the seismology community in the Philippines has been doing while the rest of the world was looking elsewhere. Now let us put a human inside this picture. Somewhere in the PHIVOLCS office in Quezon City, there is a duty seismologist whose job, for the past 11 days, has been to sit in front of a wall of monitors and watch traces. The traces look like long horizontal lines with spikes in them. Each spike is a piece of ground moving. Each new spike is another row added to the log. That person has been doing this since June 8th. They have watched the count climb past 100, past 1,000, past 5,000. They have watched it climb past 7,000. They know the number better than anyone on the planet, and they know that the number is not stable, because every shift they come into, the number is larger than when they left. That is what 7,461 looks like from the inside. Now, the question the daily broadcast is not asking, what actually ends an aftershock sequence? It is the central investigative question of this video, and we are going to spend the next several parts walking you through what the science actually says. The short answer, the answer we are going to spend an entire part on later, is that nobody knows in advance. The sequence ends when it ends. The instruments stop registering smaller events, the count plateaus, and at some point, weeks or months or sometimes years later, a seismologist looks at a long quiet stretch on the record and makes the judgment call that the sequence has tapered. There is no formal end date, there is no announcement, there is no all-clear bulletin, the sequence simply runs out. The longer answer involves something called a Maury's law, which is to say a mathematical description of how aftershock rates decay over time after a large earthquake, and we will walk you through that piece of mathematics in plain terms later. For now, what you need to know is this. Aftershock sequences do not stop, they taper. The difference between the two words is the entire reason this investigation exists. Let us put one more household frame on this before we move on, because the household frame is how the eye catches what the number is hiding. Imagine a bell, a heavy church bell, the kind that hangs in a stone tower above an old town square. Somebody pulls the rope hard. The bell rings. The first peal is enormous. It echoes off every building in the square, and it can be heard for kilometers. Then the bell rings again, slightly softer, because nobody pulled the rope a second time. The metal is just continuing to vibrate. The second peal fades into a third, the third into a fourth. The peals get closer together and quieter, and at some point you can no longer tell from across the square whether the bell is still ringing or whether you're imagining it. But if you put your hand on the bronze, you can still feel it humming. The Cotabato Trench on June 8th was the rope being pulled hard. Every aftershock since then has been the bell continuing to ring itself out. PHIVOLCS, in this analogy, is the only one in town with their hand on the bronze. They can feel it humming. They can count every hum, but they cannot tell you when the bronze will be still. 7,461 hums, and counting. The Wikipedia aggregated record drawing on PHIVOLCS bulletins and on confirmed USGS event entries is where most independent observers have been tracking this figure. It is not a primary source. It is a public-facing aggregation of primary sources, but every entry in it traces back to an instrument reading from a real station. When we cite the number 7461, we are citing the work of every duty scientist who has logged an event into that running tally for 11 straight days. We are citing real measurements of real motions of real ground, and here is where we leave part 2 open for what comes next. 7,461 is not a random number. It is a measurable consequence of something that happened on June 8th on a specific stretch of seafloor along a specific tectonic boundary that has a name almost no one watching this video is going to recognize. To understand why the count is this high, you have to understand the structure of the fault that did this. Not in the way a textbook would tell you, with diagrams and arrows, in the way the rock itself is telling you, if you know how to listen. Let us introduce you to that structure now. Part 3, the fault that has not finished talking. Let us introduce you to something most Americans have never heard of, and most Filipinos live on top of every single day. It is called the Cotabato Trench. The Cotabato Trench is a long, narrow gash in the floor of the Celebes Sea, running along the southwestern coast of the Philippine island of Mindanao for roughly 300 kilometers. At its deepest point, the trench plunges more than 7,000 meters below sea level, which is to say nearly 4.5 vertical miles of open water and seafloor between the surface of the ocean and the bottom of the gash. Standing on the deck of a ship directly above the deepest part of the trench, you would be looking down through more water than the entire vertical span of Mount Everest above sea level, in reverse. That is the geography. Now let us tell you what the geography is doing, The Cotabato Trench exists because the floor of the Celebes Sea is slowly being shoved underneath the island of Mindanao. The technical term for this is subduction, which is to say one tectonic plate sliding down and beneath another along an inclined surface. In this specific case, the Sunda plate, which is the piece of the Earth's crust carrying most of Indonesia and the southwestern Philippines, is moving toward the Philippine Sea Plate at a rate of roughly 7.3 centimeters per year, with the Philippine Sea Plate slipping down and underneath. 7.3 centimeters per year, which is to say faster than your fingernails grow, slower than your hair grows, and almost exactly the same speed at which the moon is moving away from the Earth. It is a rate of motion you cannot see. It is a rate of motion you cannot feel. But it never stops, and it never has stopped, for as long as the geology of the region has existed. That is the engine. Now let us tell you what the engine is storing. When two pieces of the Earth's crust are pressed against each other along an inclined surface, they do not slide smoothly, they lock. Friction along the contact surface, called the interface, prevents the upper plate from sliding cleanly over the lower one. Year after year, decade after decade, the plates keep moving at the deeper levels where the rock is hotter and behaves more plastically. But near the surface, the interface stays locked, and the upper plate begins to deform. It bulges, it compresses, it stores energy the way a steel spring stores energy when you press it between your hands. That stored energy has a name. The science calls it elastic strain. Now imagine a steel spring being compressed for 100 years. The pressure on your hands keeps climbing. The spring keeps getting harder to hold. At some point, either your grip gives out, or the spring fails, and either way, all the energy that went into compressing it for a century comes back out in less than a second. That is what an earthquake on a subduction zone is. It is 100 years of compression undoing itself in a few seconds of motion. The Cotabato Trench had been doing this for a long time. The technical mechanism for what happened on the morning of June 8th is called thrust faulting. A thrust fault is the kind that occurs when one block of rock is shoved up and over another along a relatively shallow angle. The upper block, which is to say the side of Mindanao itself, is forced up and away from the trench. The lower block, the descending slab of the Sunda plate, slides further down and underneath. The vertical motion at the seafloor, which is what generates a tsunami when one of these events happens under the ocean, can be measured in meters, sometimes more. The horizontal motion can be measured in tens of meters. All of it happens in seconds. In plain language, the side of Mindanao jumped up, the seafloor next to it dropped, and the column of seawater sitting above the seafloor had to do something with the gap. USGS, in its technical summary of the June 8th main shock, identified the rupture as occurring on the subduction zone interface between the Sunda and Philippine sea plates, with a focal mechanism consistent with thrust faulting at the depth and orientation expected for this section of the trench. That is the credibility source. That is not a journalist describing it. That is the agency that catalogues every significant earthquake on the planet, looking at the seismograms from every station in the world that picked the event up, modelling the motion of the fault surface, and saying, yes, this is the trench doing what the trench does. The 1976 event did this. The 1918 event before it did this. The unnamed prehistoric events that left their record in the sediment cores did this. The June 8th event did the same thing they did, on the same stretch of seafloor, by the same mechanism. The words thrust fault and subduction zone interface do not communicate motion to a person who has not seen them on a diagram, so picture it differently instead. Take two stacks of paper, lay them on a table, end to end so the edges touch. Now press them together from both sides, slowly, while pushing one stack slightly under the other. For a long time, the papers just compress. The stack on top buckles slightly. The stack on the bottom curls down at the edge. Nothing dramatic happens. But the energy you are applying through your hands is going into the paper. It is being stored. Now keep pressing for another minute, then another. Then keep doing this for 100 years, except instead of paper, it is rock. And instead of your hands, it is the slow, ceaseless motion of one piece of the Earth's crust against another. At some point, the friction along the contact between the two stacks gives. The upper stack snaps forward, the lower stack snaps down. The motion is small relative to the size of the stacks, but the energy released is everything you have been storing for 100 years, coming out in a fraction of a second. That is the mechanism. That is what happened along the Cotabato Trench on June 8th. Now we have to tell you something about what we do not know, because honest science is exactly that. Seismologists can model the rupture surface from the seismogram data, and the modelling for the June 8th event suggested that a section of the fault interface roughly 150 kilometres long and somewhere between 40 and 60 kilometres wide had slipped during the main shock. That is a piece of rock the size of an American county, a piece of seafloor and crust larger than the state of Delaware, all moving together in a single coordinated motion that lasted somewhere between 40 and 90 seconds. But here is the part the modelling cannot tell you with precision. How much of the locked stress along that section of trench actually released? The instruments can measure how much energy came out at the surface. They cannot measure directly how much energy is still locked in. Estimates from comparable subduction zone events around the world suggest that a major thrust event releases somewhere between 40 and 70% of the locked strain along the ruptured section, with the remainder either redistributing to adjacent sections of the fault or staying right where it was, waiting for the next failure. That percentage matters. It is the difference between the sequence tapering off in weeks and the sequence handing off to another large event somewhere along the same boundary in months or years. We will return to that question in part 11. For now, hold the geometry in your head. A trench, 300 kilometers long, running parallel to the southwestern coast of Mindanao. A plate sliding underneath at a fingernail's pace per year, locked at the surface for over a century. A rupture, somewhere between 150 kilometers long and 40 to 60 kilometers wide, releasing somewhere between 40 and 70% of the stress on June 8th in less than a minute and a half. And an aftershock sequence now 11 days in, with 7,461 tremors logged, still trying to redistribute the stress that the main shock did not fully release. This is not random. None of it is random. Every single one of those 7,461 tremors is the rock around the rupture surface, adjusting to its new shape, finding a new equilibrium, settling like a pile of stones that has just been kicked by a child. The big stones have stopped rolling. The small ones are still finding their places. A farmer named Romulo lives about 80 kilometers north of where the June 8th rupture is believed to have begun. We are not using his real surname because he did not ask to be in this video, but the man exists and the experience is documented in field reporting from the days after the main shock. Romulo has lived on the same parcel of farmland for 41 years. He told a Philippine field reporter in the days after the 8th that he had felt the ground shake hundreds of times in his life. He had felt earthquakes that knocked dishes off the shelf. He had felt earthquakes that woke the children. But he had never in all 41 years felt the ground simply refuse to be still. Every few hours, he said, the legs of his chair would tap against the floor, sometimes for a second, sometimes for 10. He had stopped getting up to check. He had stopped looking out the window. He had begun, instead, to count. That is the human scale of what the Cotabato trench is doing. The trench is talking. Romulo is counting. The instruments are too, and the count, 11 days in, has reached a number nobody printed. But the trench has done this before. It has done it bigger. It has done it deadlier. To understand what we are watching unfold on the screen tonight, we have to go back to the morning of June 8th itself and walk you through the math the government already had by the time the sun came up. Part 4, the math everyone got wrong on June 8th. By the time the shaking stopped on the morning of June 8th, the Philippine government already knew this was not an ordinary earthquake. The main shock came in at magnitude 7.8. That is the figure PHIVOLCS published, that USGS independently confirmed, and that became the headline number around the world before the dust on the coastal road was settled. A 7.8 is not a 7.0. A 7.8 is not a 7.5. The moment magnitude scale is logarithmic, which is to say each step up the scale represents not a doubling of energy but a 32-fold increase. A 7.8 releases roughly 8 times the energy of a 7.0 and about 3 times the energy of a 7.5. In the global record, magnitude 7.8 events occur, on average, once or twice a year, somewhere on the planet. They are the size that flattens cities when they happen underneath one. They are the size that makes oceans behave in ways oceans should not. They are the size that becomes a generational memory for the people who survive them. That is what hit the southern Philippines on June 8th. The official casualty figures, as compiled in the days after the event from provincial disaster management offices and confirmed through the National Disaster Risk Reduction and Management Council, came in at 78 confirmed dead, 1,399 injured, and 30 missing. 3 numbers, each of them is a person, multiplied. Each of them comes attached to a family in a specific province. let us walk you through the province-by-province breakdown, because the geography of the death toll is itself a piece of evidence about what the fault did. The hardest-hit provinces were Sarangani, South Cotabato, and Davao Occidental. Sarangani sits at the southern tip of Mindanao, fronting onto Sarangani Bay and the open Celebes Sea. South Cotabato is the province directly to its north and west, inland. Davao Occidental runs along the southern coast facing the Sulawesi waters. All three of these provinces face directly into the rupture geometry of the Cotabato Trench. All three of them sit on coastline or near coastline land that, when the fault moved, was the first to receive both the ground shaking and what came after the shaking, because the ground shaking in this event was only half of the story. The other half was the water. When a thrust fault under the ocean lifts the seafloor, the column of water sitting on top of the seafloor has to lift with it. The water is incompressible, which is to say it cannot simply absorb the new shape of the floor underneath. The water rises, and because the rise happens over hundreds of kilometers of seafloor at once, the wave that propagates outward is not the kind of wave a swimmer in a bay would recognize. It is long, it is low, it is fast. In deep water, a tsunami wave can travel at the speed of a jetliner, with a wavelength of hundreds of kilometers between crests and a height above the normal sea surface of only a meter or less. A boat at sea, directly over a tsunami passing underneath it, would feel only a gentle rise and fall and might not notice the wave at all. But the wave changes when it reaches shallow water. The front of the wave slows down as the seafloor rises toward the coast. The back of the wave, still in deep water, keeps moving fast. The wave compresses. The water column piles up on itself. The same energy that was spread across a wavelength of hundreds of kilometers in the deep ocean gets squeezed into a height of meters at the coast. And the wave arrives at the shoreline not as a curl that breaks, the way an ordinary ocean wave does, but as a rising wall of water that just keeps coming. That is what arrived at Calamansig. Calamansig is a coastal municipality in Sultan Kudarat province, sitting on the eastern shore of Moro Gulf, facing more or less directly into the rupture zone of the June 8th event. The tide gauge at Calamansig recorded the highest documented tsunami signature anywhere along the affected coastline. The maximum wave height above normal sea level was logged at 1.94 meters. The inundation distance, which is to say how far inland the wave penetrated past the normal high tide line, was measured at 163 meters. Those two numbers need a comparison most people can actually picture, because on their own, they can sound abstract. 1.94 meters of wave height is roughly the height of a tall man standing on a kitchen floor. Imagine the entire ocean rising as a flat-moving wall until it is taller than the man, and then moving inland at the speed of a sprinting horse, except instead of one horse, it is a wall, and it has the entire weight of the Celebes Sea pushing it from behind. That is what 1.94 meters of tsunami wave height looks like at the moment of impact. 163 meters of inundation is roughly the length of an American football field, plus the end zones, plus the back of the second end zone, plus another 20 paces. That is how far inland the water moved before it stopped. Anything sitting between the normal high tide line and 163 meters back from it was inside the water. Houses, roads, vehicles, livestock. People who had been standing on what they had always thought was dry land. This was not the largest tsunami in the recorded history of the Philippines. This was not the deadliest. But it was real, it was measured, and it was the direct physical consequence of a piece of seafloor moving along the Cotabato Trench in less than 2 minutes. The 78 confirmed deaths from the event were distributed across drowning, building collapse, falling debris, and the secondary consequences of the shaking itself, such as fires from broken gas lines and motor vehicle accidents on damaged road surfaces. The 1,399 injured included a wide range of severities, from people who were treated and released within a day to people who were still in hospitals weeks later. The 30 missing, at the time of compilation, included people whose bodies had not been recovered from coastal debris fields and from collapsed structures in the most heavily damaged areas. Each of those numbers is a name on a list, in a provincial office somewhere in southern Mindanao. Each name on the list is a household that received a knock on the door. Each household that received a knock is now part of the long, slow tale of recovery that begins when the news cameras leave. Now hold the numbers in your mind. 78 dead, 1,399 injured, 30 missing, 1.94 meters of wave, 163 meters of inundation, 3 provinces named in the bulletins where the damage was concentrated. These are the figures the math produced. These are the figures the agencies signed off on. These are the figures the headlines used in the first 48 hours and then, as the news cycle moved on, mostly stopped using. But there is something the figures on their own are not telling you. A magnitude 7.8 earthquake on a major subduction zone is not a once-in-a-lifetime event for the Philippines. It is not even a once-in-a-generation event for this specific fault system. The Cotabato Trench, and the broader subduction zone of which it is a part, has produced earthquakes of this size before. It has produced earthquakes larger than this before. The last time it did, the death toll did not stop at 78. The last time it did, the death toll climbed into the thousands. The question sitting underneath all of this is the one nobody on the daily broadcast asked. If the fault that did this on June 8th has done it before, and has done it bigger before, then what does the historical record actually say about what this stretch of ocean is capable of doing again? That answer is in the next part. We are going back to 1976. Part 5. The last time this fault did this. Remember the fault we just introduced you to. Now let us take you back 50 years to the last time it did something this large. On the morning of August 17th, 1976, at 3 minutes past midnight local time, the seafloor under Moro Gulf moved. The earthquake was assigned a magnitude that has been refined several times in the decades since, with modern reanalyses placing it at magnitude 8.0 on the moment magnitude scale. That is a 7.8 multiplied roughly by 2. That is, on the logarithmic scale that governs earthquake energy, the difference between a single firework and a coordinated display. It was a major event by any global standard, and at the time it was the largest earthquake to strike the Philippines since the instrumental record began. The death toll has never been precisely fixed, because the geography of the disaster made counting impossible. The accepted figures, drawn from Philippine government records and from the major international scientific reviews conducted in the years afterward, put the death toll between 5,000 and 8,000 people, 5 to 8,000. Most of those deaths did not come from the shaking. They came from the tsunami that followed the shaking, which struck the coastal communities along Moro Gulf within minutes of the rupture, in the dead of night, while almost everyone was asleep. Let us put that human scale on the screen for a moment. The communities along Moro Gulf in 1976 were, in many cases, fishing villages built directly on, or just behind coastal beaches. Houses on stilts, houses with palm thatch roofs, houses with families of 6 and 8 and 10 people sleeping in single rooms, because that is how rural coastal Philippines was built in 1976. When the wave arrived, it arrived in the dark. There was no warning system in place that could have given the residents the seconds they would have needed to move uphill. There was no concrete seawall. There was no upper floor on most of the structures. The wave came in, and the wave went out, and when daylight came, entire villages were not there anymore. The figure of up to 8,000 dead, attached to the Moro Gulf earthquake of 1976, is the figure that historians of natural disaster in the Philippines write down as the deadliest in the country's recorded history. That is the comparison case sitting on the shelf behind every PHIVOLCS bulletin issued since June 8th. That is the precedent the duty seismologists in Quezon City have in their heads while they watch the aftershock count climb. Now here is the second part of that comparison, the part we promised you in section 4. June 8th of this year, the magnitude 7.8 event we walked you through in the last part, has been described by Philippine seismologists and by international observers as the strongest earthquake to strike the Philippines since the 1976 Moro Gulf event. That is not a small statement. It is not a casual description. It is a 50-year benchmark, and an entire generation of Filipinos has lived its full adult life between the 1976 event and the 2026 event without seeing anything on this scale. That benchmark is doing two things at once. The first thing it is doing is telling you something about how rare an event of this magnitude is in the Philippine record. Earthquakes of magnitude 7.0 and higher occur regularly across the archipelago because the Philippines sits at the intersection of multiple tectonic plate boundaries. But earthquakes of magnitude 7.8 or larger on this specific subduction system are spaced widely enough in time that a person can be born, grow up, raise a family, and reach late middle age without experiencing one. That is the scale on which this fault produces its largest events. The second thing the benchmark is doing is more uncomfortable. It is reminding you that this fault, the broader subduction system along the southwestern flank of Mindanao, has now produced two confirmed magnitude 7.8 or larger events in a 50-year window, 1976 and 2026. Both events were thrust mechanisms along the same general subduction interface. Both events generated tsunamis. Both events killed people along the same general coastline. The mechanisms are not identical, the rupture surfaces were not identical, and we are not going to overstate the case by saying that the same exact patch of fault has now ruptured twice. The 1976 event involved a section of the subduction zone closer to Moro Gulf proper. The 2026 event involved a section closer to the Cotabato Trench. But they are part of the same broader system. They are part of the same broader inventory of stress that has been accumulating along this margin for at least the last century. That is the scientific link. Now picture what that actually looks like, standing on the ground. Imagine a long shelf, 300 kilometers long, mounted on the wall of a house. The shelf is loaded with stones. Each stone represents a section of fault that has been storing stress for 100 years. Every so often one of the stones falls off. The falling stone is an earthquake. The shelf does not collapse. The other stones do not move. But the stone that fell off is gone, and the empty spot on the shelf, while it does not look like anything, is now part of the geometry of the next loading cycle. Eventually a different stone falls. Decades pass between fallings, sometimes 100 years, sometimes more. The 1976 stone fell. The 2026 stone fell. How many stones are still on the shelf? Nobody can give you a precise count. The mapping is too coarse and the cycles are too long. But the inventory is not empty. The system is not done. Now let us go back further than 1976, because the Philippine subduction record is longer than the human memory of it. On the morning of August 15, 1918, an earthquake struck off the southern coast of Mindanao with a magnitude that USGS, in its modern catalogue reanalysis, has placed at 8.3 on the moment magnitude scale. 8.3. That is, on the same logarithmic scale, roughly 3 times the energy of the 1976 Moro Gulf event, and on the order of 11 times the energy of the June 8th event we just walked you through. 8.3 is the kind of magnitude that, in the global record, occurs only a handful of times per century, anywhere on the planet. The 1918 event was, by every measure available to modern reanalysis, one of the largest earthquakes ever recorded in Philippine history. The casualty figures from 1918 are imprecise. Because the country was still under American colonial administration, the population in the affected coastal regions was sparse compared to today, and the record-keeping standards of the era were not what they would later become. But the magnitude itself, sitting in the USGS catalogue as a confirmed historical entry, tells you what this stretch of ocean is capable of doing. It has done 8.3, it has done 8.0, it has now done 7.8. The question this leaves open is uncomfortable, and we will not pretend it is not. If the same broader subduction system has produced a magnitude 8.3 in 1918, a magnitude 8.0 in 1976, and a magnitude 7.8 on June 8th of this year, then the historical record is showing you a fault that is capable of producing events larger than what just occurred. It is showing you that the June 8th event, dramatic as it was, is not the upper bound of what this fault can do. That does not mean another 8.0 is coming next week. That does not mean another 8.3 is coming next year. It means only what the record itself says. This stretch of ocean does this. It has done it bigger. It will, on some timeline that no agency can pin down, do it again. That is the historical parallel. That is the inventory. And that context raises a harder question this investigation has not answered yet. How many more stones are still sitting on that shelf? Part 6. 35 earthquakes. Since 1900, USGS keeps a running tally for every earthquake zone on the planet, and the tally for this one is not comforting. The agency, which is to say the United States Geological Survey, maintains a global earthquake catalogue that goes back more than a century. Every confirmed earthquake of magnitude 4.5 or greater is entered into the catalogue, with a location, a depth, a magnitude, and a date. For events of magnitude 7.0 or greater, the agency also maintains a curated subset, because magnitude 7.0 is the threshold above which an earthquake reliably produces damage, casualties, and broader regional consequences. The catalogue is searchable by geographic radius. You can ask it how many earthquakes of magnitude 7.0 or greater have occurred within any chosen distance of any chosen point on the Earth's surface since the beginning of the instrumental record. So we asked it that question for the location of the June 8th main shock. Within a 300-kilometer radius of the June 8th epicenter since the year 1900, USGS has recorded 35 earthquakes of magnitude 7.0 or greater. 35. 126 years of record. An average of one major earthquake on this stretch of ocean every 3.5 years for as long as the instruments have been measuring. That is the tally. Now let us put the household frame on it. Imagine you live next to a busy intersection. The intersection has a traffic light. Most of the time the light works. Most of the time traffic flows smoothly, but every 3.5 years on average the light fails and a major collision occurs at the intersection. You would not say you live near a safe intersection. You would not say the failures are random and unforecastable in a way that makes the geography irrelevant. You would say, with full justification, that the intersection has a problem and that the next collision is somewhere in the inventory of time, even though you cannot give the date. 35 major earthquakes since 1900 within a single 300-kilometer radius is the seismological equivalent of that intersection. The fault system here is not quiet. It has never been quiet. It has been producing magnitude 7.0 and larger events at an average pace of one every few years for the entire span of the modern instrumental record. Anchored inside that tally is one event in particular, the one we mentioned at the end of the last part, the magnitude 8.3 of August 15th, 1918. That event sits in the USGS catalogue as the largest single earthquake on this stretch of ocean in the 126-year instrumental record. It is the upper benchmark. It is the high water mark. Everything else in the catalogue of 35 events is smaller than it, but the existence of an 8.3 in the record, only just over a century back, tells you what the system is mechanically capable of producing. Let us put the 8.3 into the same household scale we used for the 1976 event. A magnitude 8.3 is approximately 5.5 times the energy of the June 8th event. It is approximately 3 times the energy of the 1976 Moro Gulf event. On the global stage, an 8.3 is the kind of earthquake that, depending on where it occurs, can rewrite the coastlines of nations. The 1918 event in the Philippines did not produce a casualty figure on the scale of the modern era, because the population exposure in that region in 1918 was a small fraction of what it is today, but the energy was real, the motion was real, and the record of it sits in the USGS catalogue as a permanent reminder that this fault, once a century or so, produces something on that scale. 35 events at magnitude 7.0 or larger, one event at magnitude 8.3, 126 years, one single radius of 300 kilometers. This stretch of ocean does not forget how to do this. Look closer at the texture of those 35 events, because the average of one every 3.5 years is hiding the rhythm. Earthquake recurrence is not a metronome. It is not a clock striking the hour. The 35 events are clustered. There are decades in the 1920s and 1930s where the catalogue shows a pair of large events within a few years of each other, followed by a decade of relative quiet. There are stretches in the late 20th century where the count thickens around the 1976 event and the years immediately on either side of it. There are periods where the system seems to be storing rather than releasing, and then there are periods where the system seems to be releasing rather than storing. Both of those phases are part of how a major subduction zone works. Among the seismological community, the rhythm has a name. It is called a seismic cycle. The cycle is the alternation between strain accumulation, which is to say the years and decades when the plates are moving against each other and the interface is locked, and strain release, which is to say the events themselves, when sections of the interface break and the stored strain is liberated as seismic energy. The cycle on a major subduction zone like the Cotabato Trench can run anywhere from a few decades to several centuries between the largest events on any given section of the interface. The intermediate events, the magnitude 7.0 to 7.5 range, can recur more frequently as different sections of the zone slip at different times. 35 events, 126 years, a cycle that varies in length but never stops cycling. Now let us put a single human inside this number, because the figure of 35, on its own, is too long a list to hold in the mind. Consider an elderly woman living in General Santos City in South Cotabato. Call her by her age. She is 73. She was born in 1953. In her lifetime, just inside that 300-kilometer radius, USGS has recorded somewhere in the range of 15 earthquakes of magnitude 7.0 or greater. 15 events the size that closes schools, cracks buildings, and ends lives. She remembers some of them more vividly than others. She remembers the 1976 event the way an American her age might remember a major hurricane that came ashore over her childhood home. She remembers smaller events the way you remember a particularly bad snowstorm. She has lived inside the seismic cycle of the Cotabato Trench for her entire life, without ever using the word seismic cycle, and she could tell you, without referring to any catalogue, that the ground in this part of the world does this. It always has done this. It is doing it now. This is the human scale of 126 years of catalogue data. It is the woman in General Santos who has seen 15 of the 35 events with her own life. Now pivot the lens back to the present. The 7,461 tremors of the current aftershock sequence are not an entry in the catalogue of 35. They are the tail of one entry. The June 8th main shock is event number 35. The aftershocks are the rock around event 35 settling into its new shape. But every event in the 35 event catalogue had its own aftershock tail. Some of those tails were brief, some of them lasted years. The 1976 event produced aftershocks that were still being recorded into 1978. The 1918 event in the imprecise records of the era was described as having produced felt aftershocks for months. The current sequence, 11 days in and still climbing past 7,461, is on a trajectory that is consistent with the larger events in the historical record. That is what the catalogue is telling you. The June 8th main shock is in a category of events that this stretch of ocean produces, on average, every 3.5 years. The aftershock sequence is in a category of tails that, for the larger events in that catalogue, has historically run for months or longer. The number 7,461, in that context, is not an outlier. It is on schedule. The question, Part 6 leaves open, is the one that runs underneath the entire investigation. If the catalogue is showing you 35 major events since 1900, and an 8.3 sitting at the top of the inventory, and a current aftershock sequence climbing past 7,461 with no end in sight, then what does the agency that watches all of this actually say about when the sequence stops, when the danger window closes, when a normal life is permitted to resume? The honest answer is in the next part, and the honest answer is the hardest one to put on television. Part 7. The question. PHIVOLCS will not answer with a date. Let us ask you a question that, when you first hear it, sounds like a riddle. When does an earthquake actually end? The main shock ends when the shaking stops. That part is straightforward. The fault surface ruptures, the energy radiates outward as seismic waves, the waves pass the observation point, the ground returns to rest. For the main shock itself, the end is measured in seconds, 40 seconds, 90 seconds, 2 minutes at the outer edge. The instruments record the beginning of motion, the peak of motion, and the decay of motion, and the main shock is, in the technical sense, complete. But the earthquake is not the main shock. The earthquake is the entire sequence. The main shock is the headline. The aftershocks are the body of the article, and the body of the article does not have a known length when you start reading it. PHIVOLCS, the Philippine government agency charged with monitoring the country's seismic activity, has been issuing daily bulletins on the June 8th sequence since the morning of the main shock. Every bulletin contains the same kind of information: magnitudes, locations, depths, tectonic origin, expected damage, aftershock advisory. The aftershock advisory line on bulletin after bulletin has used a single recurring phrase: aftershocks could persist for several days to weeks. Days to weeks. That is the official forecast. That is not vague language meant to hedge a known answer. That is the most precise statement the agency is able to make. There is no bulletin coming, on any specific date, that will say, the aftershock sequence ended at 6 this evening. There is no date in the calendar that PHIVOLCS has circled, behind which the duty seismologists are quietly waiting for the count to plateau. There is no model running in the back office that can tell anyone, with any meaningful confidence, when the 7,462nd aftershock will be the last one. This is not a cover-up. This is not bureaucratic caution. This is the actual state of the science. Let us walk you through why, because the honest explanation matters. Storms, the kind of weather event a 65-year-old American watching this knows well, can be forecast with meaningful confidence days in advance. The National Hurricane Center can tell you, with reasonable accuracy, that a storm is going to make landfall on a specific stretch of coast within a window of 12 to 24 hours. The forecast is not perfect. The cone of uncertainty is real, but the underlying physics is well understood. The atmosphere is observed by satellites and by aircraft and by surface stations, and the equations governing how warm, moist air moves over a rotating planet have been refined for decades. You can stand in a kitchen in Florida on a Wednesday and know, with high probability, that the wind will be inside the door by Saturday morning. Earthquakes do not work that way. The fundamental difference is not a matter of effort or funding, it is a matter of physics. The atmosphere, where storms live, is a fluid that scientists can observe in real time at every altitude across the entire planet. The crust, where earthquakes live, is a solid that scientists can observe only at the surface. The interior of the rupture zone is invisible. The state of stress along the fault interface, at depths of 30 or 40 or 100 kilometers below the seafloor, cannot be measured directly. It can only be inferred from what comes out after the fact in the form of seismic waves. You can observe the bell ringing. You cannot observe the bell. This is the limitation. It is the same limitation that every seismological agency on the planet operates under. USGS operates under it. The Japan Meteorological Agency operates under it. The Chilean and Peruvian and Mexican seismological services, the Italian, the Turkish, the Indonesian, every one of them. The science of earthquake forecasting in 2026 can tell you where earthquakes are likely to occur. It cannot tell you when. What the science can do is describe the rate at which aftershocks decay. There is a mathematical relationship, named after the Japanese seismologist Fusakichi Omori, who first described it in 1894 after the Great Nobi earthquake. The relationship is called Omori's law, which is to say a description of how the frequency of aftershocks per unit of time decreases roughly in proportion to the inverse of the time elapsed since the main shock. In plain English, if you had one aftershock per hour on the first day after the main shock, you might have one aftershock per 2 hours on the second day, one per 3 hours on the third day, and so on, with the pace tapering toward but never quite reaching zero. Omori's law is a description of behavior, not a prediction of a stop date. The law tells you that the rate will decay. It does not tell you when the rate becomes indistinguishable from the background seismicity of the region, which is to say, the normal low-level rumbling that the Cotabato Trench produces even in years when no major event has occurred. The decay can be steep, it can be shallow, it can be interrupted by what seismologists call secondary aftershock sequences, which is to say, a moderate-sized aftershock that itself produces its own smaller aftershocks. Each interruption resets the local rate. Each interruption extends the visible tail. The current sequence, 11 days in, is still well within the window, where Omori's law predicts an elevated rate. The decay has begun. The peak intensity, which was in the hours and first day after the main shock, has passed. But the rate at day 11 is still higher than the long-term background. That is why PHIVOLCS continues to put aftershocks expected on every bulletin. That is why the official forecast says days to weeks rather than days or weeks or months. Days to weeks is the truth. Let us put a household frame on this, because the abstraction of decay rates is hard to hold. Imagine you drop a heavy bowling ball into the center of a deep, still swimming pool. The ball goes under. The water explodes upward in a column. The column collapses. Waves spread outward to the edges of the pool. The waves bounce off the edges. They come back. They cross. They interfere with each other. The largest motion is in the first few seconds. After that, the motion fades, but the water is not still. For minutes after the ball entered the pool, you can see the surface rippling. You cannot point to a single moment in advance and say, this is when the surface will be still. You can only watch the rippling decrease second by second, until at some point you look at the surface and realize you cannot tell anymore whether the small motion you are seeing is left over from the ball, or whether it is just the wind on the water. That is what the end of an aftershock sequence looks like. It is the moment when the small motion left over from the main shock becomes indistinguishable from the normal small motion of the region. There is no single second at which the transition occurs. There is only a gradual fade and a retrospective judgment, weeks or months later, that the fade is complete. Now we want to bring you to the emotional center of this investigation, the peak, the single statement that is the honest verdict of the science, applied to the question every viewer is sitting with right now. They do not know how many more. They do not know how strong. They do not know when it stops. Read those 3 sentences again. They are not rhetorical. They are not literary, they are the actual condition of the forecast. The agency that monitors this fault, with the most complete data set, the most experienced duty staff, and the deepest historical familiarity with the system, cannot give you a count of how many more aftershocks are coming. They cannot give you a maximum magnitude for the next aftershock. They cannot give you a date for when the sequence ends. That is not failure. That is the science telling you the truth. So what does watching actually look like when you cannot give a date? It looks like duty scientists on shift in Quezon City, around the clock, reviewing every event as it logs into the system. It looks like field teams in the affected provinces, performing on-the-ground damage assessments. It looks like daily bulletins, every one of which contains the same phrase. It looks like government coordination meetings in which the question, "Is it over yet?" is asked and not answered. It looks like a nation, holding the line on its emergency response posture, not because anyone has told them an event is imminent, but because no one has been able to tell them an event is impossible. That is the answer to the riddle we opened with. When does an earthquake actually end? Nobody watching tonight, including the duty scientists themselves, can tell you what that watching will still find. Part 8. 2 earthquakes. One morning, 2 different warnings. Remember the 2 earthquakes we opened this investigation with. One buried 95 kilometers down, one sitting almost at the surface. Here is why that difference matters more than the number does. In part 1, we walked you through the basics. 2 events, same morning, same date on the calendar, June 18th, same magnitude reading on the USGS catalogue, 5.3, same general country. But 2 different depths, and therefore 2 different things being said by the same fault system, at almost the same moment, to 2 different audiences on the ground. That is not a coincidence. That is a system. Set the 2 events side by side, because that comparison is where the real diagnostic value sits. A duty seismologist looking at the June 18th record sees one magnitude 5.3 at 95.3 kilometers depth near Kablalan, and a separate magnitude 5.3 at roughly 10 kilometers depth near Bobon. Both are real, both are confirmed, both are part of the broader aftershock sequence of the June 8th main shock. But they are sourced from 2 different parts of the broader system, and they are telling the seismologist 2 different things about how the system is settling. The deep event at 95.3 kilometers is happening inside the descending slab. Think of the slab as the piece of the Sunda plate that has been pushed under Mindanao by the subduction process. As the slab descends, it bends. As it bends, the rock inside it experiences enormous compressive and tensile forces. At certain depths, the rock fails in response to those forces, producing intermediate depth earthquakes. The June 18th Kablalan event was an intermediate depth event. It was not happening on the interface between the 2 plates. It was happening inside the slab itself, deep below the surface, as the slab responded to the new stress distribution created by the main shock. The shallow event, at 10 kilometers, is a different animal. It is happening at the interface, or in the upper crust just above the interface, where the 2 plates meet. A shallow event in this geometry is almost certainly part of the direct aftershock sequence of the June 8th main shock, the kind of event Omori's law describes, the kind of event that occurs as the rock surrounding the original rupture surface adjusts to the new geometry. 2 events, 2 sources, 2 different parts of the same broken system, both still moving. Now here is the part where the depth difference reshapes the experience on the ground. Let us walk you through it carefully, because the implications for the people standing on the surface above each event are not the same. For the deep event, the shaking footprint was wide and the intensity was modest. The energy of a 5.3 originating at 95 kilometers depth has to travel through 95 kilometers of rock before it reaches the surface. Along the way, the rock absorbs energy. The rock scatters energy. The rock filters out the higher frequencies, which is to say the sharp, fast vibrating components of the seismic wave that do the most damage to brittle structures, and lets through mainly the lower frequencies, the long, slow rolls. A person standing directly above the rupture might feel a noticeable but not violent shaking, lasting longer than they would expect with a low rumble in the chest. A person 300 kilometers away might feel something similar, dimmer but still present. For the shallow event, the situation is the opposite. A 5.3 originating at 10 kilometers depth puts much of its energy into the high frequencies. The shaking is sharp. The intensity at the surface, directly above the rupture, is significantly higher than the same magnitude event at depth. The footprint is small. A person standing on the surface 10 kilometers from the rupture point feels a hard vertical strike. A person 50 kilometers away might feel almost nothing, or might feel only a brief jolt. That is the depth difference translated into the language of bodies standing on the ground. Now let us go one step further into household scale, because the words high frequency and low frequency do not communicate the felt difference to a person who has never been inside an earthquake. Imagine you are sitting in your living room on a couch. Somebody upstairs drops a heavy object onto the bedroom floor. The thump travels down through the joists, through the drywall, through the air, and reaches you as a low, dull boom that you feel as much in your chest as you hear in your ears. The whole house shudders for a moment. That is the deep event. The energy has been filtered by the building, and what arrives in the living room is muffled, broad and brief. Now imagine instead that the heavy object was dropped directly onto the floor of your living room, 2 feet from where you are sitting. The thump is no longer dull. It is a sharp, hard crack. The floor moves under your feet. The lamp on the side table jumps. The water in the glass on the coffee table splashes. That is the shallow event. The energy has not been filtered by anything. It arrived at you in its raw form, and it shook the things closest to it harder than anything farther away. Same source. Same magnitude, 2 different floors, 2 different experiences. The bulletins PHIVOLCS issued for the 2 June 18th events reflected this. The bulletin for the Kablalan event noted that the shaking was likely felt across a broader area, with no expected damage, consistent with a deep intermediate depth source. The bulletin for the Bobon event noted that the shaking was likely felt locally with greater intensity, also with no expected damage, given the magnitude, but with a more focused footprint. Both bulletins continued the standing aftershock advisory. Both noted that further events should be expected. 2 warnings, 2 different bulletins, same morning, same fault system. That is not 2 earthquakes. That is 1 fault system, finding its new shape in 2 different places at once. Now here is the diagnostic reading of the 2 events together, the kind of read a seismologist makes when they look at a daily activity map. The presence of a deep intermediate depth event in the slab, on the same day as a shallow event on the interface, tells the duty scientist that the stress redistribution from the June 8th main shock is not contained to one zone. It is propagating. The slab is responding at depth. The interface is responding near the surface. Different parts of the broader system are still finding their equilibrium, and they are doing it on different schedules. That is consistent with what an aftershock sequence of this size looks like. That is also why the official forecast remains aftershocks expected. One more picture will make this concrete, because the abstraction of stress redistribution can lose its grip on the listener. A family in Kablalan, on the morning of June 18th, sitting at the breakfast table, felt the deep event as a long rolling motion that made the coffee in the cups slosh sideways, and lasted long enough for everyone to look at each other before it ended. They knew what it was. They had felt dozens like it over the past 11 days. They went back to their breakfast. A different family, 50 kilometers away near Bobon, felt the shallow event minutes later as a sharp, hard jolt that knocked a framed photograph off a shelf and brought the dog up barking. They also knew what it was. They had felt a different texture of motion over the past 11 days, the texture of the shallow events, the ones that came as a quick punch instead of a long roll. They picked up the photograph. They went back to their morning. 2 families, 2 different shakings, same fault, same morning, same day in a sequence that, 11 days in, has produced 7,161 of these readings, in every depth, in every part of the affected zone, in every texture of motion the rock is capable of making. That is what the 2 June 18th events, taken together, are telling you. The system is not done, the slab is still adjusting, the interface is still adjusting, the number is still climbing. But the shaking is only the part anyone can feel. The part that takes longer to register is what it left behind in the offices nobody points a camera at. Part 9. What 13 courthouses tell you that no seismograph can. Long after the cameras left General Santos, 2 government institutions were still quietly telling the truth about how unfinished this disaster is. The first institution is the Supreme Court of the Philippines. In the days following the June 8th main shock, the court issued a series of administrative orders suspending the operation of courts across 13 cities and provinces in the affected region. 13. The list included the major urban courts of General Santos, the provincial courts of South Cotabato and Sarangani, and the regional and municipal courts of Davao Occidental, Sultan Kudarat, and several adjacent jurisdictions. The suspensions were not symbolic. They were not gestures of solidarity. They were practical responses to a set of physical conditions, which is to say, damaged courthouse buildings, displaced staff, blocked transportation routes, and ongoing aftershock risk that made the resumption of normal court operations unsafe and unworkable. That is not a single news cycle's worth of disruption. That is institutional time. The second institution is the Bureau of Internal Revenue, the Philippine equivalent of the American Internal Revenue Service. In the same window, the BR issued an extension of tax filing and payment deadlines for taxpayers in General Santos, Sarangani, and South Cotabato. The agency cited the disaster directly, recognizing that businesses and individuals in the affected provinces would be unable to meet standard deadlines, and providing an administrative window for the resumption of normal compliance. The extension was not a small administrative tweak. It was a formal recognition, encoded in a published order, that the basic mechanisms by which a working economy operates, including the timely payment of taxes, had been disrupted by the earthquake and its continuing aftershock sequence. These two actions, taken together, are doing something the daily news cycle is not doing. They are measuring the actual length of the disaster on the only timescale that matters to the people who live inside it. Not the timescale of the headline, the timescale of the recovery. Let us put a household frame on this, because the distinction between headline time and recovery time is the entire point of Part 9. Imagine a hurricane makes landfall on a stretch of American coast on a Saturday afternoon. By Sunday evening, the cameras are everywhere. By Monday morning, the major networks are leading their broadcasts with images of damage, interviews with residents, and helicopter shots of flooded neighborhoods. By Wednesday, the story has moved off the front page. By the following Monday, the network coverage has slowed to brief check-ins. By the end of the second week, the cameras have moved on entirely. But the courthouse in the affected county is still closed. The local IRS office is still extending deadlines. The schools are operating on reduced schedules. The hospital is still triaging. The county clerk is still recording damage assessments. 2 weeks in, 6 weeks in, 6 months in, the institutional life of the affected area is still rebuilding itself from the storm long after the cameras left. That is the difference between headline time and recovery time. The Philippine situation is on the recovery time clock. The Supreme Court of the Philippines is operating on the recovery time clock. The BIR is operating on the recovery time clock. The duty seismologists at PHIVOLCS are operating on the recovery time clock. The headlines, by now, have largely moved on. This is not unique to the Philippines. This is what natural disasters look like everywhere. The visible part of the disaster, the part the cameras cover, is the smallest part of the actual event. The larger part is the institutional unwind that follows, and the institutional rewind that eventually rebuilds. Both of those phases take months or years. Both of those phases are conducted almost entirely off-camera. Now consider what the 13 courthouses are actually closed for, because the closures themselves are evidence. A courthouse is a physical structure with specific requirements. The building must be structurally sound because lives and case files are inside it. The building must be accessible to the public by routes that are themselves safe. The staff who operate the courthouse must be able to reach it, which requires that their homes, their transportation, and their childcare arrangements be intact. The witnesses, the defendants, the lawyers, the jurors, all of them must be able to travel to the building on the appointed day. If any one of those conditions fails, the courthouse cannot reliably hold a proceeding. If multiple conditions fail at once, the suspension is not optional. In the affected provinces of southern Mindanao, all of those conditions failed simultaneously on June 8th, and many of them have not yet been restored. The Supreme Court's order recognized that. The order was not a single suspension with a fixed end date. It was a set of suspensions by jurisdiction, with provision for extension as the situation warranted. The court was not pretending it knew when the courthouses would reopen. It was setting up an administrative framework under which the reopening could happen as soon as conditions allowed, and not before. Inside that framework, every day a courthouse remains closed is a day the institutional life of the province is not normal. Civil cases are not being heard. Criminal proceedings are paused. Land disputes are unresolved. Family law matters are deferred. Bail hearings, contract enforcement, the entire machinery of civil society that ordinarily runs in the background of a province's daily life, has been put on hold for the duration of the institutional emergency. Multiply that by 13 jurisdictions. That is the scale of the institutional disruption. The BIR extension is the same kind of evidence, in a different form. Tax compliance is the connective tissue of a functioning economy. The fact that an entire tier of provincial taxpayers needed an extension means that an entire tier of provincial businesses and households were physically or financially unable to meet their normal obligations during the affected window. The extension is, in effect, a measurable indicator of how many people were knocked off their economic footing by the main shock and its continuing sequence. Put a single human inside this picture for a moment. A small business owner in General Santos, running a hardware store on a commercial street that suffered moderate damage in the main shock. Before June 8th, she had a standing schedule, monthly tax filings on a known date, quarterly remittances on a known date, daily inventory checks, supplier deliveries, payroll for 3 employees. After June 8th, her storefront has a cracked front wall. Her supplier in another province had its warehouse damaged. Her bank branch is operating on reduced hours. Her bookkeeper's home is uninhabitable, and the bookkeeper is now staying with relatives across the city. Her own apartment lost water service for 9 days. The BIR extension is not a gift to her. It is the government recognizing formally that the conditions of compliance, which is to say the existence of a stable business operating in a stable environment, do not currently exist for her. The extension buys her the institutional space to rebuild before she has to file. That is what one institution looks like from the inside. Multiply it by every taxpayer in the 3 named provinces. That is the institutional scale of what the Supreme Court and the BIR are quietly acknowledging. This is the real measure of an ongoing disaster, not the camera footage, not the headline magnitude, not the count of confirmed deaths in the first week. Those are the visible markers, the ones the daily broadcast can put on screen in 30 seconds. The real measure is the institutional clock, the courts, the tax filings, the schools, the hospitals, the land registry, the shipping schedules. Every one of those systems carries a calendar of its own, and the calendars have been disrupted, and the disruption is the disaster, continuing under the radar of any television camera. The seismograph can tell you when the ground is moving. The seismograph cannot tell you when the courthouse will reopen, and nobody covering this story tonight is asking who actually can. Part 10. The broadcast skipped. Here is the part no broadcast interrupted to mention. On the morning of June 18th, when the magnitude 5.3 event hit near Kablalan, and a separate magnitude 5.3 hit near Bobon, the international news cycle reported each event the way the news cycle reports any earthquake, as a single isolated occurrence. A few hundred words of wire copy, a graphic with a map and a magnitude, a line noting that the Philippines is still recovering from a recent larger event. What none of those reports included was the number that recontextualizes every word in them. 7,461. That number was not concealed. It was not classified. It was not buried in a restricted document. It was and remains available on PHIVOLCS' public bulletin feed, on Wikipedia's regularly updated aggregation of the sequence, on the wires of any reporter who took the additional 5 minutes to look. The reason it did not appear in the broadcast coverage of June 18th is not because someone hid it. The reason it did not appear is more ordinary and more uncomfortable. It did not appear because the daily news cycle is not built to carry an 11-day-old running total alongside a fresh breaking news event. The producer working on a 30-second wire story about a 5.3 earthquake has a job to fill the slot, identify the location, attribute the magnitude, and move to the next story. The producer is not paid to walk the viewer through the prior 11 days of seismic context. The producer is rewarded in the modern news economy for speed and brevity. Brevity does not contain 7,461. This is not a conspiracy. This is institutional caution and daily news cycle pressure, operating exactly as they were designed to operate. But the consequence of that design is what brought you to this video, because the viewer at home, watching the standard wire story about a 5.3 earthquake in the southern Philippines, walks away from that story with a wrong picture in their head. They picture a single isolated event. They picture a country that is recovering, which is a word that implies the worst is behind. They picture a moment in the news, which is a moment that ends when the producer goes to commercial. They do not picture an aftershock sequence 11 days deep and 7,461 events tall. They do not picture 3 magnitude 6.0 or greater events buried inside that sequence. They do not picture a duty seismologist on the night shift in Quezon City, watching the count climb past 7 PHIVOLCS 61 towards 7 PHIVOLCS 62 and towards 7 PHIVOLCS 63, and toward whatever number it reaches by the time you finish this video. That is the gap. That is the part the broadcast skipped. It skipped it for ordinary reasons. It will skip it again tomorrow when the next aftershock crosses the 5.0 threshold and gets its own brief wire story. It will skip it next week when a different country has a more dramatic event and the editorial attention moves elsewhere. The gap is not malicious, it is structural, and the only way around it is the kind of long-form, full-context reporting that the daily cycle does not have the time or the space to do, so we have done it. The point of Part 10 is not to indict the news cycle. The point is to name, plainly, what the news cycle does not contain, and to leave you with the corrected picture in your head. 2 earthquakes on June 18th, of magnitude 5.3 each, at different depths and in different parts of the broader Cotabato trench system, are not isolated events. They are aftershocks, 7,460 and 7,461, in a continuous sequence that began on June 8th with a magnitude 7.8 main shock that killed 78 people, injured 1,399, and displaced communities across at least 3 provinces. They are part of a sequence that has produced 3 earthquakes of magnitude 6.0 or greater so far. They are part of a sequence that has not ended. They are part of a sequence that PHIVOLCS, the responsible agency, says could continue for days to weeks, with no fixed end date. That is the corrected picture. That is the part the broadcast skipped. But the corrected picture still leaves the hardest question in this entire investigation untouched. Part 11. The number that is still climbing. Remember where we started. 7,461. That was the number on the morning we began this investigation. That was the figure on the PHIVOLCS bulletin, on the aggregated public record, on the running tally of every confirmed aftershock since the morning of June 8th. That was the count attached to the magnitude 5.3 earthquake. The headlines reported as if it were the first thing happening in the southern Philippines that morning. It was not the first thing. It was the 7,461st thing. And here is the truth this investigation has been moving toward from the opening sentence. By the time you finished watching this video, the number has almost certainly changed. The duty seismologist on shift in Quezon City has logged additional events into the running record. Some of them were too small to be felt by anyone. Some of them were felt by farmers in Davao Oriental, by families in Sarangani, by the small business owner in General Santos whose hardware store still has a cracked front wall. None of them were large enough to make the international news cycle. All of them were real, all of them were part of the same sequence, all of them belonged to the same number. The count did not stop while we were talking. The count never stops while anyone is talking. That is the honest condition of the story. There is no agency on Earth that can tell you what number that aftershock count stands at this exact second. PHIVOLCS cannot. USGS cannot. The duty scientists who watch the readings in real time can give you the number as of their last bulletin, but the next event might be logging into the system as they speak. The number is not a snapshot. The number is a moving point on a curve, and the curve, 11 days in, is still well above the long-term background rate for this fault system. The sequence will end. That is not in doubt. Every aftershock sequence ends. Omori's law, the description we walked you through in Part 7, guarantees that the rate will continue to decay. The bell will eventually be still. The water in the pool will eventually return to its surface tension. The 7,461st event will eventually be the second to last, or the 50th to last, or the 500th to last instead of the latest. But the sequence will not end on a date that any agency has the ability to give you in advance. It will end the way sequences always end, quietly, without an announcement, without a press conference, without a single bulletin that says the sequence has concluded. It will end when a duty seismologist, weeks or months from now, looks at a long stretch of recording showing only the normal background rate of the region and makes the judgment that the elevated activity from the June 8th main shock has tapered to a level indistinguishable from what the Cotabato Trench would be doing in a year when nothing had happened. That judgment has not been made. That judgment cannot be made yet. The number is still climbing. And so we close this investigation the way the honest answer requires. 7,461 is not the end of the count. It is simply where the count stood the moment we stopped watching, and nobody, not USGS, not PHIVOLCS, not the people of Mindanao standing on that ground tonight, can tell you the number it will be tomorrow.